This video describes the system developed by researchers from MIT to compete in the Virtual Robotics Challenge held in June 2013. Our approach was centered around the concept of Tele Automation, in which an operator provides high-level instruction on short timescales to a simulated model of the Atlas robot from Boston Dynamics. This instruction was provided through our 3D user interface. The interface presented a rendering of the state of the robot and its environment and enabled the creation of plans which could be communicated to the robot and achieved using our full-body controller. Mimicking real-life operation conditions, the challenge limited communication between the user and the robot. To overcome these limitations, we integrated LiDAR data on short timescales to create a series of projections, depth maps of the robot's workspace, and height maps for footstep placement and situational awareness. Actionable objects of interest, known as affordances, were defined by simple primitives. Owing to a significantly constrained uplink, plans sent to the robot were compressed using custom algorithmic entropy encoder based on the Gobi project. This resulted in a compression ratio of over 30:1 for robot plan messages. All of this enabled the user to retrieve a high-fidelity rendering of the environment, updated at low rate, and to send detailed plans for interacting with that environment. The two main modes of our planning and control infrastructure were manipulation and walking. During manipulation, the operator requested the sensor data, fit object models, and generated robot plans. To initiate the manipulation of an object, a hand grasp was synthesized to create force closure. Next, our whole-body motion planner produced a reaching plan to place the hand at the desired grasp location. Once the object was grasped, we generated a manipulation plan to adjust the object's degrees of freedom. This manipulation planning framework allowed our team to perform all of the object manipulations required by the VRC. Grasping and lifting a hose, connecting the hose to a pipe, and turning a flow valve were all accomplished in the competition environment. The walking mode of our interface balanced automation of simple walking behaviors with fine footstep interaction for difficult environments. Our operator indicated a desired location for the robot as a navigation goal, and the footstep planner created a safe set of steps from the robot's position to that goal. Our walking planner used these footstep locations with a simple dynamic model of the robot to compute a stable feedback controller and a full-body motion trajectory that the user could review before the robot commenced execution. During review, the operator could adjust individual foot placements to avoid difficult terrain and control the precise walking motion of the robot when necessary. Due to the low drift rate of our state estimator, continuous LiDAR fusion allowed our controller to also modify its foot placement while in motion. When walking failed due to collisions or unstable interaction with the terrain, a series of recovery motions allowed the operator to direct the robot back to standing or into our dynamic quadrupedal crawling gait. With a combination of walking and crawling, the MIT robot reached the end of the VRC walking task in all 5 of the competition runs. Our team will continue to apply the principle of Tele Automation as we prepare for the physical competition in December 2013.